So what we did in our previous video was find the lower sum for a particular region using n rectangles, and now I want us to find the upper sum. So I'll remind us of what we're doing. Find here, we're just trying to find the upper sum. We already found the lower sum for the region bounded by the graph of the function x squared and the x-axis between x equals 0 and x equals 2 using n rectangles. Okay, so now we're finding the upper sum. So if you remember, in our last video we found delta x, the width of our rectangles, it was 2 over n. And remember, we had our picture of our region. So here I have 0 to 2. And then say this is 4. So here's my function. And I want this region underneath this graph and above the x-axis. So I want, in particular, the region that's inside of here. So now, let's look here. If we're talking about upper sum, we're talking about an overestimate. So if I'm looking at my first rectangle, to get an overestimate, I need to find it using the right endpoint. So if I go here and use my right endpoint, you'll see that my rectangles go above my graph. So here, if I go with the right endpoint, again, my rectangles will go above the graph. And so here, if I'm looking for an upper sum, I want an overestimate. So in this particular case, to get an overestimate, we need to use the right endpoints. So let's use a capital MI here for the right endpoints. So what's our first right endpoint going to be? M1. I start at my interval, which was 0, and I add delta x to it to get my first right endpoint. So here I've gone out here, and I want to take this. And my second right endpoint, so remember that this is 0 plus 2 over n. And I'm writing 0 here again because maybe my interval doesn't start off at 0. So in that case, you'd have a number there instead of having 0. What's M2 going to be? Well, to get my second right endpoint, I go delta x out, and I go another delta x out. So it'll be 0 plus 2 delta x. So 0 plus 2 times 2 over n. If you did M3, it would be 0 plus 3 delta x. So 0 plus 3, 2 over n. And if you look for the pattern here, right, I'm trying to write capital MI here, a formula. Right, notice that this coefficient this coefficient here matches what's there, and this 2 matches this one here. There's a coefficient of 1 here that matches a coefficient of 1 there. So MI would be 0 plus I times 2 over n. which is really just 2i over n. So now that we have a formula for the right endpoints, we can find our formula for the upper sum, capital SN. That's what I'll use for upper sum. I need to add up the area of those n rectangles. So now I'm using right endpoints, so it'll be f of mi, and then the width. So again, this is the height, here, and then this is the width. Oh, I had it right to begin with, sorry. The height and the width. So let's add these up here. We're going to plug in our right endpoint formula. This is f of 2i over n, and delta x was 2 over n. And then what was my function? It was x squared. So I can now square 2i over n. So really, this becomes the summation from I equals 1 to n. This is 2 cubed over n cubed, I squared. Now this part that's in front here, that has no I in it, it's a constant, and so I can pull it out in front. So this becomes 8 over n cubed, the summation from I equals 1 to n of I squared. And now we use our summation formula for this summation here. So look back at your formula. This is n plus 1, 2n plus 1 over 6. And then if you multiply out the numerator, you will get 2n cubed plus 3n squared plus n over 6. You'll get 8 over, and then if you distribute here and simplify, you'll get 8 over 3 plus 4 over n plus 4 over 3n squared. And this is the formula for my upper sum. So if you compare this with the lower sum, so just remember what was our lower sum. Our lower sum was 8/3 minus 4 over n. If you'll see, the upper sum is going to be bigger, right? Because everything has positive coefficient there. But down here, everything has negative well, not everything. This middle term has a negative coefficient, so it's going to be smaller, which makes sense because remember, the lower sum is an underestimate, so it should be smaller than our overestimate. And if we also remember that we took the limit in our last video. If I took the limit of my lower sum, it was 8/3. What happens when I take the limit of my upper sum? Here, the limit as n goes to infinity. Well, you're going to get 8/3 as well. The other two terms are going to give you 0. So this term will give you 0 and this term will give you 0 because the denominator has larger degree. And so it turns out that if as n goes to infinity, your lower sum and your upper sum become closer. And if I take the limit, I get the same number. So that happens in general. That's what's called the limits of lower and upper sums. So in general, if I look at the limit as n goes to infinity of Sn of the lower sum, it's the same thing as the limit of the upper sum.